Hello, today we are going to talk about solving by factoring and discussing multiplicity of roots and the fundamental theorem of algebra and how they apply to polynomials. So multiplicity you can read here, but the overall idea is how many times a root or a zero appears in an equation as a solution is going to be the multiplicity. So a answer appears 2 or 3 times, and that's going to have a multiplicity of 2 or 3 depending on the problem. So looking at this example, if we were to solve this p of x equals x squared minus 6x plus 9, we can factor that to say x minus 3 and x minus 3. And so you can see per the textbook equation up top that that factor appears twice. So you can either use this and say that there's a multiplicity of 2. We could also rewrite it as x minus 3 squared, which would have that, or we could solve out all of these to say x minus 3 is equal to 0 using the zero product property, and we would get x equals 3 and x equals 3. So we know that our root of 3 or our 0 of 3 occurs twice, so it has a multiplicity of 2. So we're going to solve these, and we're going to find the multiplicity of each 0. So looking at number 1, it's already in factored form for us, so it's 3x squared times the quantity x plus 5 raised to the 4th times x minus 4 is equal to 0. So we're going to use the zero product property to solve. So we're going to say 3x squared is equal to 0, x plus 5 to the 4th is equal to 0, and x minus 4 is equal to 0. So this is, when we solve this, we're going to divide by 3 and then take the square root. Well, dividing by 3 is going to give us 0. Square root of 0 is 0. So we're going to get 0. However, we should see that this square root means that we were actually going to end up with x equals 0 twice. So we can write underneath there that we're going to have a multiplicity of 2 on that, because we really have like x equals 0 and x equals 0 if we were to write out all of the possible solutions. The same goes for the next one, was we could write this out as x plus 5 times x plus 5 times x plus 5 times x plus 5. But we don't want to have to do that every single time. So we can just automatically just go x plus 5 is equal to 0. And we will get x equals negative 5. And then we should see that we have this happening 4 times. So then our multiplicity would be 4. Because it occurs 4 times. There's 4 of that factor in the original problem. The last one we can just solve to say x equals 4, and that would be a multiplicity of 1. So we could write it out this way for each root and write the multiplicity. An easier way or a more organized way could be to say we find the zeros and the multiplicity on the bottom. So we're going to say 0, negative 5, and 4. And so 0 occurs twice. So the multiplicity is 2. Negative 5 occurs 4 times, and 4 occurs 1 time. So we can write it either way. You don't have to do both. Looking at the next one, we can solve this by factoring. If we have 4 terms, we can group. So we're going to take an x squared out of the first group. We're going to take out a minus 9 out of the second group. So we're going to end up with x plus 3 and x squared minus 9. And since we're solving by factoring, we want to keep factoring that to say x plus 3 and x minus 3. So you can see that x plus 3 occurs twice, or when we set this equal to 0 using the zero product property, you're going to see that we get negative 3 twice as a final answer. So we get x equals negative 3, x equals negative 3, and x equals positive 3. When we write our chart, we want to, or if we were to write it all together, we would need to make sure that we say that negative 3 only happens 1 time in our chart or in our final answer, but it has a multiplicity of 2, and that 3 has a multiplicity of 1. So that's something that we need to make sure that we recognize, or else it is kind of defeating the purpose if you were to list it out multiple times as a multiplicity of 1. Building off of that, we have something called the fundamental theorem of algebra. So this is going to apply for the rest of time when you deal with algebra. And it's fundamental, so it's a pretty important thing if they call it that. But the main idea that we're taking away is the first two pieces for today. So if we have a degree n, then we're going to have exactly n solutions. So a third degree polynomial will have 3 solutions. We could have repeated solutions, but we're still going to have 3 solutions, and that's what the multiplicity says in the second part. The last two pieces are what we'll talk about later on in the unit, but it just means that if you have an imaginary or complex number as a solution, you know the conjugate will also be a solution. And the same thing is true with like a plus the square root of b. You're also going to have the conjugate of that. And if you think about the quadratic formula, which applies to the polynomials only, but you're going to have that negative b plus or minus the square root. This is kind of taking into consideration of that, but it's going to work for all polynomials. So we're going to still solve the kind of same way that we've done before, but we're going to state the multiplicity of each year, and then we're going to state the degree. It'd be kind of easy to see the degree of this one just because of the original problem. If you know your vocabulary, you know our degree will be 7. But you're going to see that the multiplicity should add up to that, which will also be helpful, especially if we were to go back to the first examples. So if we factor out first the GCF of x to the 4th, it's going to leave us with x to the 3rd minus 5x squared minus 25x plus 125. We want to factor by grouping inside the parentheses. So we're going to be left with x to the 4th. This is x squared. This is the GCF of that, and we get x minus 5. We can take out a minus 25 out of the second group, and that's going to leave us with x minus 5. Keeping x to the 4th on the outside, we're going to end up with x minus 5. And then x squared minus 25. Again, we want to continue factoring, not solving by the square root if possible. So that's going to be plus 5 and minus 5. So when we solve this, we're going to get x equals 0, but it's going to happen 4 times because we have x to the 4th right there. We're going to get x equals 5, x equals negative 5, and x equals positive 5. So if we were to make our chart, and they ask for roots and zeros are the same thing, their terminology that are referring to the same thing. So if we make our chart, 0 occurs 4 times because we have that x to the 4th, and then positive 5 occurs twice, and then negative 5 occurs 1 time. And then we should know that our degree is going to be 7 because of the original problem like we said, but we should also be able to add up 4 plus 2 is 6 plus 1 is 7. So we could use that idea to go back to something like 1 that's in factored form, and we don't know what the degree is. That's not a second degree polynomial, but if we were to FOIL everything out, we would end up with 2 plus 4 plus 1, so that would be a 7th degree polynomial, but we don't need to FOIL out for that. Lastly, we have another factoring problem. We're going to set this equal to 0, and so we're going to say x squared and x squared to get our x to the 4th, and then we're going to say minus 5 and plus 1. We can't factor this any further, so we're going to solve this by square roots. By using the zero product property, we get the square root of 5, so plus or minus, and here we should get square root of negative 1, which is plus or minus I. When we write this out, we need to be careful in how we do it, in that plus or minus root 5 cannot go into our table. We need to say root 5 as one solution, negative root 5 as another, because those are two separate solutions. Same with our I and our negative I. And then we should know that each one of these happen or occur 1 time. And so again, our multiplicities should add up to be our degree, which is 4 in this case. And we should know that this is a 4th degree polynomial from the original problem, but also from our multiplicities. So I hope this helps in showing how we can solve by factoring today and use that to discuss multiplicity and fundamental theorem of algebra.